So we're going to spend a little time today talking about relays, contactors and starters, and some digital logic, a little bit about ladder logic, and give you a couple opportunities to work through some problems on kind of like on paper, some labs that we've got in here. So a few of you, I think Matt, you've run through this relay course, right? Jeff, did you come through this one? You have, okay. So for the most part then, this will be pretty new for everybody, although you've probably, at least to some degree or another, played around or done something with relays. Okay. The whole purpose for all of this is so that you're better able to troubleshoot wiring diagrams, schematics, things like that. So we're going to start here first talking about relays. On the screen and on your very first page of the handout, the top left corner and the middle diagram of the top are two ways of drawing a relay that we typically work with. Okay. So
makes sense, you know, it's a university.
this one up here, who can describe kind of what a relay is and how it works a little bit?
Which one are you talking about?
Or just thinking relay.
So yeah, Jeff, tell us about, we're talking about these two. Describe to us kind of the principles behind what a relay is and how it works.
You have a coil that's got some conductors in it that energize it, creates a magnetic field, pulls down the hammer, which is usually an iron core or something. It's built inside there, closes a set of contacts, energizes it, sends you power through your conductors to whatever you're trying to control.
Okay, great.
Does that set it up?
That sounds good.
Yes.
Okay, so we have a coil that's essentially depicted by like this little curly Q wire with a couple lines next to it. A lot of times that refers to a iron core type of a electromagnet. Sometimes we'll see them, and oftentimes we see them drawn more like this in our drawings. There's a circle with either a C in the middle, sometimes a CR, sometimes there's other indications, a letter or number. Both of these relays that are depicted here are a Form C relay. But are there any differences between those two drawings? Can anybody tell me a difference between this and that one in the functionality? Okay, so they do the same thing, right? Just a couple different ways of drawing them. I have a common coming into one side, which would be this here. And then I have a normally open, which is depicted with what? Two parallel lines.
Yeah.
Normally closed is parallel lines with a diagonal through it. Okay? So normally closed or normally open are in reference to what?
De-energized, no power.
Okay, so there's no power
To the
applied
coil.
to the coil. I could have power on either side of the contact, but typically we're talking about when the coil is not energized. So coils come in different voltages. Some are DC, some are AC. The ones that we typically work with in the control world are 24 volts AC. Now we do run into 120 volt a bit as well, but a lot of the stuff that we'll touch are 24 volt AC for the coil. Does that mean that the contacts have to be 24 volts AC?
No.
Okay, no. They could be any voltage, right? They could be a DC 5 volt, 10 volt. They could be a milliamp signal even. Sometimes we've done that. But usually there'll be some other voltage. They could be 24 volts. We use that quite a bit. Sometimes 120 volts. We try to do all of our 120 volt switching on newer panels will be outside of the panel. Do 24 volts inside. We try to keep the higher voltage out of the panel. Some of the older panels, did we have 120 in the panel? Did we switch 120 in the panel? Yeah. You just got to be very careful. So don't just assume that it's all low voltage if it's in the panel. Okay. These are labeled here, at least this one shows a Form C. What do we mean by Form C? That's not something you probably hear a lot unless you're working with relays a lot. Anybody know what a Form A or a Form B is? Relay.
Would it have to be with a socket or its shape?
Okay, it's a good possibility, but in this case, it has reference more to what's available. So Form C has both a normally open and a normally closed contact. A Form A would just have normally open. Form B would be just normally closed. Okay, Form C has both. And so that's kind of the way that they're described.
So how many forms are there?
3. That's at least the 3 common ones are A, B, and C. So, and you think of like a light switch, that's typically like a Form A. It's normally open, we flip the switch, and it closes it, and then it turns the light on. It could be also a Form B, because it's closed one way. It's kind of like if we energize it and it closes, that would be a Form A. If we energize it and it opens, that's a Form B. And so by closing means electrons can flow, or we've got electricity flow through that switch. So, with relays, they're pretty basic, right? I think most of all of us have worked with kind of a single relay or maybe even a couple relays at a time, and that's not too hard to troubleshoot and figure out what's going on. How do I troubleshoot a coil of a relay versus a contact? If I have a meter, what are some things I can do to troubleshoot to see if a coil is working correctly? Okay, so which would you start with?
Right, voltage.
Okay,
Yes.
so voltage, because typically it's in a circuit that's powered. Not always, but a lot of times. So if I put it on voltage, what type of voltage, AC or DC?
Whatever it calls for.
Okay, what is it calling for?
On the coil?
Yeah,
Well,
it depends on the circuit.
depends on the circuit you look
Yeah.
at it.
So if the circuit is one that we know that's got a 24 volt transformer, 120 volt, we're probably going to be AC. We'll start there, and very rarely do you see DC circuit in control world, but we do have it. We have 0 to 10 outputs, and sometimes we'll use those outputs to switch on a relay that's a DC coil. Not very often, but sometimes. So put it on 24 volts. What should I see, and how do I measure it?
It's energized 24 volts.
24 volts.
So I'm going to put my leads one on either side of the coil connection, right? And I should see that across. What if the coil, I see 24 volts across it, but the coil's not working?
If there's current going through it, you would not get 24 volts.
Yeah.
Ah, there we go. Okay. What will I get across it?
Hopefully 0
Okay.
or very low voltage
Are you sure?
all the time.
Actually, no.
You will see 24 volts across the coil,
Across the
Is this
coil, but not the
common in-
contactors.
not across the contacts, right? Because remember, it's a load.
Did you
If
have
it-
a comment on it?
So
If
the
it-
meter measures potential amount.
The load will have a voltage drop across it.
Okay. It will.
Right. So if it's not powered, you will measure a short between it with an ohm meter,
Yeah, okay.
or a very low amount of resistance, right? It will be 15 ohms, 20 ohms, something like that. It's a very low amount of resistance. And the resistance in that coil is dependent on the voltage that's applied to it, right? If we put a 24 volt coil in a 120 volt circuit, what happens? Doesn't last long, right? It usually, the smoke goes out pretty quick. Okay, or vice versa. If I put a 120 volt coil in a 24 volt circuit, what happens?
Not enough to pull it in.
Yeah, it won't pull the contacts in. It can't generate enough of that electromagnetic field to make the electromagnetic part work. So it doesn't work. So, but yeah, so you'll have, when you put your meter across it, 24 volts if it's a 24 volt circuit, 120 if it's 120. And you should see it because it is a load. There is a drop in voltage there.
If the coil is open, then won't your meter still pick up 24 volts because you got potential?
That'd be a difference of potential.
You would, because you're going across.
Say that
you're
again?
You're bridging it.
If you're going across the coil and the coil is open, you'll still get 24 volts.
Yeah.
So that's not a very good way to test a coil.
You will see if you got voltage there, and that's about it. You won't necessarily know if the coil's pulled in.
Okay.
So true. So yeah, if the coil has burned up and it's, got an open in the circuit, you would also see 24 volts there. Okay.
But
But-
either way, you're.
You at least verify that you've got
Contact.
voltage there, and then it's a matter of does the voltage match what the rating of that that coil is. So, okay. Contacts, how do we troubleshoot contacts?
Figure out if it's normally open or normally closed.
You can
And then
only
go
measure
between.
the voltage
So do we ohm it out when
on
it's in the circuit and powered up?
Sure do.
Yeah, it happens, right?
Some people.
Then you get a new meter.
Just a new fuse.
That's the way to get
It depends. Sometimes it becomes a fuse issue, sometimes not. So,
Meter fuse.
usually we want to start with voltage if you're going across contacts, just to be sure. But it's always best to troubleshoot a contact. You can troubleshoot them powered up, but use volts, not ohms.
Yes.
Okay. If you need to go where you want to check continuity, then you can do that, but do it once you've powered down the circuit. Okay. Welcome. All right. So we've got a couple things up here in the upper right that motor contactor and starter. Okay. A contactor typically is just a way of turning a motor on and off. A starter typically has a few other components in there to protect the motor. And we're going to look at this piece down here. We'll scroll down to in a minute. It's a little more involved starter. But this contactor up here, the M in the circle up at the very top represents what?
Contacted wall.
So it's the coil, all right? Much like the C is in the middle right here. That C in the circle is representing the coil. The M is representing the coil of our starter. Now we have 3 M's next to the parallel lines, meaning open contacts. What are those telling us?
Meaning they're all three switched, right?
Okay, yeah.
Part of the same coil.
Normally
So
open,
M-
yeah.
M is the open contact was the M
So
coil.
they're all related to the coil that's also labeled M. Okay. Now with a 3-phase motor, which is what this is indicating, we've got 3 legs of power. Why do we want to close all contacts at the same time or open them at the same time?
It's a 3-phase motor.
Yeah, you
burn it
don't
up.
want to use single phase
That's right.
and cause issues with that motor, you'll burn it up.
All right, so why, so single phase in a motor, does anyone feel they understand what that really means enough to explain it to the group?
Well, you have 3 legs on a 3-phase motor. If you single phase it, you're only having 2
Yeah,
phase,
you've only got
2
two cycles
legs
out of
bringing power into the motor.
Okay. So if we were to look at this, if say for instance L3 goes away, the way that I get power through a motor is going from L1 to L3, L1 to L2, L2 to L3, right? It's taking 2 of them, they're wound and then connected. That winding, even though it looks like a dead short because it's an inductive motor, we don't burn it up. They're built to work that way. But if I get rid of one of those 3 legs, I lose actually 2 of the sets of windings. Okay, so I only have 1 set of windings now that's working, so a single phase. The other 2 go away because I don't have a way to finish the path. When you single phase a motor, typically we have 3 phases working to turn this mass, this it takes a lot of power. If I only have 1 phase, the motor has what's called slip. In other words, it can't keep up. The rotating magnetic field gets ahead of the motor because it's heavier. I don't have all 3 sets of windings helping to keep it going. And as I get more slip, it increases the current draw. And so what happens is the current draw goes up and up and up, and eventually will burn up the set of windings of the one good phase that's left, and it'll burn it out, okay? So that's single phase in a motor, and that's why it's not ideal. We don't
Doesn't
want that
last.
to happen.
Doesn't last.
Motors don't last long, especially if we have this kind of a starter, right? If we have a contactor, what do we gain?
Get
What-
an
what are
over- get
these
an
here?
overload in there.
You still have internal overloads on
Yeah.
that three-phase
They,
motor.
they do, they have,
It's gonna
some-
kick in and kick out, you won't
Yeah.
hear it. It's still gonna short-live the motor, right?
it can really damage
So-
it, in some cases it can ruin it totally,
Right.
true.
If it's a solid
Especially
state
on the
internal
compressor or
overload
something like that.
is what they've gone to now, no longer it clicks on, right?
Right.
So,
Okay, so, but these overloads here are designed to protect the motor, people, or both.
oh,
More the motor, more the motor than anything.
So what do these do, these overloads? What is their purpose?
open up in case of heat.
High current.
Seeds the heat due to high current.
Okay, so the old days, we had what we called heaters, right? It was a kind of a metal
Still
little
do.
clip in and
Yeah.
pop in thing.
We got plenty of them all around.
Yeah,
Have a
there's still
solder-
lots.
Have a solder pot.
And the little solder pot that basically gets to the melting point that's determined for that size, it melts through and it breaks the overload, which then opens that up, right? And it basically takes out the ability for the motor to turn. We shut all three of those contacts down at the same time. Nowadays, we have electronic overloads, and so they're resettable. We don't have to physically remove
And they're
a
quick,
piece,
too.
put a new one in.
Resettable.
They're adjustable,
Just,
and so that's very handy as well, so that we can adjust them to, you know, like if the motor is changed out and we need to turn it up or down, we can do that, okay? So, do overloads protect people?
No, because you can still get several cycles.
Okay,
Before
overloads
they-
are
before it
not
opens up.
designed to protect me or you,
No.
okay? You ever touched an old motor that has a zap to it on the case? Shouldn't. But if, you
Just
remember some
a
of
little
those?
tingle.
You get a little, you touch them and they kind of, you're like, whoa, there's a little, so that could kill you. The overloads will probably never trip in that case, okay? So they're not designed, that's not the function of an overload, it's to protect the motor, the windings of the motor, so. Okay, any questions or any comments about motors or the overloads or contactors, at least to this point? All right. So this guy here is closer to what we're gonna see in most of our, you know, it depends on the type of the motor control centers we have. We'll have the buckets, we'll have, you know, handoff auto switches. Some of them may have start stops. Most of the ones we have nowadays have handoff autos. But if it is, this is, I think, what they call an interposing contactor or starter. They have a few things in here that we haven't talked about that we want to cover. Okay. First off, here's our bottom. This bottom piece is what we were looking at above. What is this piece right here that's tied into L1 and L2?
That's the primary side.
primary, secondary.
Okay,
Power
so
for your transformer.
so that symbol is a symbol for a transformer.
Right.
Okay, transformer.
Different voltages on this.
Yeah, so in this case, we're probably going from a higher voltage to a lower voltage, could be 480 to 120 is a pretty typical, you know, 4-to-1 ratio that they'll do on the windings. We run 120 for the control side. Okay, we're going to come back to these here, but our overload is in our kind of the safety, same like we had above. Our motor starter will basically, if that opens, the motor starter will drop out, motor turns off. We have another contact here, which is tied to this one, right? CR here, CR there. What size fuse would we expect to see in this? I'll give you some options. 10 amp, 5 amp, 1 amp, or 0.5 amp. What would you expect for this circuit?
Seems low.
No, probably
Seems
less
based
than
upon
5
that,
amps.
low of that.
Okay, I've got a 0.5,
I'd say 5 amps or less.
5 amps or less,
3,
3.
3
Okay.
Whatever you have in the drawer.
So that's why I'm asking
And
this
or a 22
question.
shell works good too.
Okay.
I'll do it.
So, a lot of times in a circuit like this, the fuse will pop and we're like, oh, I don't have any of X size, but I know I've got one that's a little bigger. Bigger's better, right? Always better. No. Okay. In this, what is the load of this circuit?
Just the coil on
The coil
CR.
and CR.
Yep.
Okay. What kind of load in amps would a coil take?
Less
At least
than what?
20.
Less
At
than
It's-
least 20.
Yeah, sure. You got a blow dryer for a coil in there?
It's gonna have an inrush 'cause
It
it's
automatically
a
opens
contact.
up itself.
It does, yes, yes.
So, okay, so that's a good point. Now, one of the things that I have found side story, we had a contactor and looked at this and like, oh, I just got the coil of this contactor. That shouldn't be much. So we put in a 50 VA transformer. Guess what? Wouldn't work. And it ended up chattering so bad that it actually ruined the core inside the windings. We had to replace it. So we got a bigger one, put a 75 VA, or 100, I can't remember what it was. Still didn't work. Burned it up again. We ended up having to put like 125 VA, 150 VA transformer in there. And it was because this can be a very big coil, right? Because I'm pulling in, if this motor is a 50 or 100 horse motor, how big are these contacts? They're big. So it's going to take a lot of power to
Probably
pull that
silver.
in. So
And the silver also.
this transformer may be bigger, so it could be up to 5 amps, okay, if it's a big transformer. But typically, you're probably more half an amp, 1 amp for the control circuit. But you got to be careful because if it's the bigger you get, the more you'll need a bigger fuse in there, okay?
It's all based upon that
Because there is an inrush,
transformer.
because you've got that delay on any type of an inductive load. So, sorry, Jeff, you were saying?
It's all based upon that load of that transformer. That's your biggest load.
Right.
there.
Well, there's the inrush, but this is what, when that
That's gonna
turns
be-
on and
That's gonna be
off.
small compared to that transformer.
So the transformer's not introducing any load. It's this coil that will.
Yeah, but you're gonna increase your heat load, just as you said, because of the contacts you're pulling on the mainline contactor, depending on what you're pulling down there, right? Because you're setting up a control relay.
Okay, so when I'm sizing this transformer, it's based on this load or inrush of that load. Okay, and that's really all that matters. This transformer, it may have some heat, it may have
So you
some,
said, you just said though, you could potentially need a 5 amp fuse based upon the load.
depends on this transformer, right?
That's what I just said.
Okay, so you said the same thing. So the size of the transformer
Okay.
is what determines the fuse. So if I'm 120 volts and I have a 240 volt transformer, what size fuse do I need? 240 volt at 120 volts, 240 VA, so I need a 2 amp, right? So I take your VA divided by the volts, that tells you the amp rating, okay? So, yeah. All right, so what's happening in this circuit?
So you push
Yeah, control relay.
So currently the motor's off.
Coil.
your stop.
What, I have 2 buttons up here, right? The stop button is normally what? Okay, and is it momentary or holding?
Momentary.
Okay, these symbols are typically the symbol for a momentary push button. I press the button and it switches from its drawn state to the opposite state. So the stop is a momentary, normally closed. And what's the start? So momentary, normally open. Okay, so if I press the start, or right now before I start it, how much, what's my voltage at 6 compared to 4? Say we're 120 volt on our secondary.
Yeah, be the full secondary.
So I'd have 120 volts at 6, right? So full voltage there, just waiting. I'd also have 120 volts at 2, waiting for that one. So I press the start, then what happens?
CR pulls in,
Okay.
which pulls in M.
So CR pulls
CR
in,
pulls in, closes CR contacts.
closes the
Energizes
contact,
the main contact.
Pulls it
which
in,
then
energizes
sets up-
there,
Motor starts and the M
Sets up its
contact up
holding
between.
circuit.
those
two and three.
close.
She
I
also
also
sets the holding
have-
circuit.
That there, what do we call that relay or that contact?
The holding
circuit.
contact.
It's a holding contact. So this is essentially a latching circuit. In other words, once I engage it by pressing the start, it has a mechanism to keep itself running or on. I don't have to keep holding the button. Okay. Now, we're running, we're going. How do I stop this?
Stop button.
Okay. Pressing the stop button, where does it stop our flow of current at?
At 5.
5, right? So 5 is basically the place where it stops. So before we were going 6 to 2, that was holding us. So then it went all the way through, but now I have no voltage there. So CR de-energizes, the contact opens, the main contactor
De-energizers.
de-energizes, those contacts all open, motor turns off. Okay, we also open here, so then if I let go of my stop, I'm seating again where I first was, where 6 and 2 have voltage there ready to go. Okay. All right. You guys run into this ever? Okay, they're out there, right? Things slightly different. You might have slightly different, but we have stuff on campus that are like this. Okay. Say, for instance, my motor doesn't start. How do I go about troubleshooting this? So the one thing that Scott said is, and you said it too, Jeff, is check L123. Now, are we technically, as AC technicians, supposed to be checking 480 volt?
No.
No.
Okay.
Somebody's watching you?
Sure you can,
Okay.
as long as
Can I
you
just
suit
suit
up.
up?
I suit up every time.
Or arc
Okay.
flash, yeah,
Always
flash.
arc flash, that's what I wear.
So, what
None to buy that
instead
too.
of the, what is, if we wanted to take maybe a slightly safer approach, what could we do to check without getting into the high voltage side?
Our
Check the
relays.
secondary voltage.
Okay, secondary. Now, it's 120, technically, really, that's even still supposed to be out of our, what we're
It
supposed
depends
to
when you
get.
show up on it. Is the coil humming? Is it humming? Is it not
Okay.
making any noise? Is there,
But
you're gonna use all kinds of different.
There's
things,
lots of
right?
ways you
So
can buy, just,
You're gonna see the coil physically be able to see the coil, see if it's energized, see if it's de-energized. You're gonna
Okay.
take a look at some contacts, see if the thing's got.
so the first thing we'll do is,
So-
we'll probably get our meter and check to see if we've got 120 or 24, depending on the, whatever our secondary is, okay? Now, fuse is good, we should have voltage up to 5, right?
Yeah.
So where am I putting my meter leads, what numbers?
4 and 5.
So 4 and 5, and my voltmeter is set to what?
Or the secondary voltage.
AC.
So AC volts, typically, right? Do we ever see DC starters? I'd be surprised on campus,
Oh, okay. Not good.
okay? There are DC starters out there.
Car.
Yeah, there's DC coils and contacts in cars that we use. But rarely are we gonna see that on campus. There may be a few instances, but usually we're gonna be AC. Okay, so 4 is our one reference point, and then as we try to troubleshoot this, we're gonna take our other lead and move it around through the circuit, right? So maybe 5 or 6 or 7, maybe 2 or 3 is where we're gonna check next as we try to troubleshoot this. Okay. Sounds good. All right. I want to flip the next page. One of the things that probably tripped me up the most when I very first got into working with relays was figuring out how this base was wired. Okay? Once you get it, it's like, oh, why didn't I get that before? It was a piece of cake. But sometimes it's like magic. It's, somehow it just comes in and goes out. Now, one thing I want to let you know is if you're not sure, ask a question, because when we have our lab on Wednesday or Thursday, I guess you guys will be Thursday afternoon, it will be really obvious if you don't get this. Okay, so if you're not getting it, ask now, because you're gonna be wiring up relays just like this. You're gonna hook up the coil, you're gonna hook up the contacts, and if you're not really certain, you're gonna try to hook up a coil instead of a common on the contact, and it's just not gonna work right. Okay? So, everyone worked with these before?
Yeah,
Seen 'em?
just a little advice, don't give somebody that doesn't know how to run one your brand new screwdriver.
He shortens them.
Blow the hole in it,
Yeah.
and then he looks at you like,
What kind of a screwdriver was that? So one thing I'll caution you,
Nice.
if you have wires on the top and bottom, and you're trying to unscrew the bottom one, and that's probably what happened,
no, he just didn't know what he was doing.
okay. If you happen to touch the coil to the other one, you'll maybe cross 24 to 120. It doesn't like that. So just be careful.
Sparky.
Okay. So on these bases, they oriented the tabs on the relay that'll plug into the socket. They orient the tabs to help us identify what's what. The ones that are by themselves, the two by themselves that are perpendicular to the others, are the coil. So that's where we're going to apply the 120 or 24 volts, or if it's a DC, we'll apply that voltage to make this relay switch from one set of contacts to another. Okay. Typically, those will be off of these top two screws if you're using our standard base type relays. Now, you'll notice internally how these are wired. The bottom screws kind of go out and come into the middle on both sides. The top screws come to the edge terminals. So if you think about it, we're not going to want to cross wires as we build these little, as the manufacturer's putting these together, they're not going to want to cross those in that. So if you're ever not sure, just remember close ones go to the top, go to the close, bottoms go to the middle. Okay. So we have our coil up here, our electromagnet, plug into these two. Then we have three other tabs for each set of contacts. So how many sets of contacts are on this one? Two or?
Well,
You have three tabs.
you
How
have
many
two
sets of contacts?
You have
Two.
Six.
Contacts.
Four.
It's a trick question.
Trick question.
It's a
No.
trick question.
Two pole relay.
Yeah, but how many contacts are
How,
there in there?
how many sets of contacts?
two sets.
Two sets.
Two sets of
sets.
contacts.
Right.
Okay,
Normally
seven.
open, normally closed.
They almost. So we have these three tabs, which tie into here, are one set of contacts. I have a normally closed. You can see this is a wiper, and it essentially swings from one side to the other as that coil is energized. So this outside is going to be what? Normally open or closed?
Closed.
Does everybody see that? It's normally closed. Because it sits there, and the wiper is touching that outside contact to that piece. As soon as I energize it, it will pull this and pull it from this outside to the one that's closer. So that would be our normally open. So normally closed are the top set here. Normally closed
Close from
are in this middle.
12 to 4.
Okay. Normally closed and then normally open down here. What are these over here? So it's the common of the contact, right? And these,
Common of the
yeah, not the common of the circuit, just common of the, and these are the coil. Now, does the coil are these or like polarity sensitive?
If your relay is.
DC.
For DC,
they
yes,
are.
but for AC, they're not. Okay. The one thing I would recommend if you're wiring a panel, put all the R's or 24 volt high, 24 volt low, the common, on the same sides consistently. Just be consistent. If you're going to number your contacts, start one here, then two, do that through the whole panel so that as somebody comes behind you, troubleshooting makes sense. Okay. All right. So this is a double pole, double throw, which is another kind of acronym that we use for these, relay. Double pole means I have 2 sets of contacts. Double throw means I have normally closed and normally open, or form C. Okay? So double throw, double pole, double throw. And sometimes how those are called. All right. So this image here is of how many sets of contacts? 4. So how would we title this one? Double throw,
4-pole double throw.
4-pole double throw. I have 4 sets of contacts, normally open and normally closed on each set. Okay? Now, this drawing is just more to help you kind of get in your head how these are laid out. My coil are going to be the 2 screws with some blank spaces between them. Does that make sense? Because those are the ones that are perpendicular to all the other sets of tabs or the holes in the base. And so I don't need anything wired to those. So these are the common side of the contact, right? So this is the schematic kind of drawing. Normally closed would be the top. Normally open would be the bottom as we're kind of going down. This would be kind of the physical look where that little wiper thing goes between the 2. Okay? Any questions? So on Thursday when you come for the lab, you may want to bring at least the first few pages. You can bring the whole thing as reference so that as you start to wire up some of these relays, if you've got questions on what's the common, what's the normally open closed, you can look back to this and this will help you. Okay. Any questions? If I'm going to hook power up to switch to some other part of my circuit, do I use the normally open, normally closed side or the common side typically?
Common side.
Okay, why? Will it work both ways?
Sure would.
If
Yeah.
you got it on the right.
If you only need one of the contacts, if I only need normally open or if I only need normally closed, I could bring R into the other side, or the power, the 24 volts. But a lot of times, there may be reasons to switch things later, so bringing our supply side into the common so we can switch it either direction works out better later on. So it's kind of it's not a rule, but it's good practice, I guess you could say. Okay? All right. Yep, we're almost ready for that. Let's talk about digital logic a little bit. How many of you have done digital logic? So up on the board over here, we have some digital logic. And tell you what, Matt, do you want to pull that screen up? Now, when I say AB, what do I mean by that? What is AB?
2 inputs or 2
Yeah,
states?
it could really be anything that we're dealing with, okay? This could be a freeze stat and a fan start stop. I mean, any kind of things that we're looking at to compare if they are working together, okay? When we do relays, we use this digital logic, which we're going to kind of go through. I'm going to leave this up on the board, but we'll write it up again here. If I'm looking for either an A condition or a B condition, we'll call that an OR. If I have both of my inputs as off, what is my output going to be? Off. That's going to be off, right? If I have A off but B on, I'm going to be on. If A is on and B is off, still on. And then what happens with both?
On.
Still on. Okay. So that's kind of what these they call this a truth table. It's just you can work through the logic and say, and we may have A, B, C, and D. We could have 3 or 4 or 5 things that we're looking at, and we can still draw this out. It gets a little bit more larger if we get more than 2. What about an AND? If A and B are off, Still off. A off, B on,
Off,
off.
Off, wrong answer.
Yeah, okay. I meant off, like that. We're off on that
Your
one.
mouth was there, your hand was
on.
I was ahead. There's two steps. And if I have both of them,
Yeah, on.
okay. So what would be an example of something like this?
Condenser unit or fan in a compressor.
Safeties, the only safety.
Okay.
Just safeties.
Safeties. Yeah,
Flow
there's-
switches, prestats.
Okay, so I'll give you just a rough, say for instance, I want to back my car out of the garage. All right, is the car started? And is the garage door open? All right, two important pieces to get the car to come back. I may even have a third if I put it in reverse. Maybe another one is, is there a car or a kid in the driveway? If not, as long as there's nothing behind me and the door's open. So there's four things, all of those have to be true to get me to back out, right? Okay. Now, there's a few others that we'll talk about, and those are, I'm going to leave those on the board, but essentially, if I have a NOR, so I have an OR, I negate it or invert it. So the NOR would be a 1, 0, 0, 0. And then there's a NAND. What do you think that looks like?
So,
1, 1, 1, 0. Okay, so they're just inverted. We have an XOR, which is really the favorite of all of them, right?
Yeah.
It's just different, right?
Beautiful.
Yeah. Why is that?
0110.
Okay. 0, 1, 1, 0. So it's what's called an exclusive OR. I have one, but not the other. One, but not the other. If I have both, I have a 0. Okay. We have an XNOR. So that's just the opposite. Okay. There's also one that's called a NOT or an invert. What would you expect that to do? So if A is 0, what's my out? 1. Or if A is 1, it just switches it from one to the other. Okay. So there's the complete list up there. This one's going to get covered up or erased, and we'll pull the screen back down. Why do we care about digital logic?
We apply it on all of our programming.
We use it in a lot of places. There's physical relays that are wired in such a way to combine these that we have in almost every one of the panels that are on campus. In software, which we're not really covering in this class, we implement software to do this kind of digital logic. Okay, so there's a lot of places that it applies and then it comes into play. So we want to make sure you kind of have a basic understanding of that before we get too far. All right, if you want to hit our screen there. Okay. We've spent some time talking about digital logic and some relays and some basics of some relays. We're going to start going through, I skipped one, didn't I? Oh, this is the best part. Yeah. We don't want to skip this because this is fun. We're going to do this first one together, and then the second one I'm going to let you guys work out. So the starter we looked at earlier has a start-stop in there, and this is the way that the drawing came. It has a 2-wire control if used. Now, if I wire this and leave everything just as it is and add the dotted, normally open contact at the top, what will this do if that is my building automation control signal?
It'll never stop.
Start up and don't stop.
Okay, so I got, from both these guys, it'll start and not stop.
unless it's told to stop.
Okay,
Unless there's a power outage.
There's gotta be something to push that stop.
okay, so let's talk about it. If my control system is a held contact, is there any way to stop this?
To de-energize it.
So if I press the stop button, will it stop if the control signal has that contact closed?
Yeah, you need to run.
It will just run, right? It'll hold it running. Now, if it's a momentary, it'll start it, but is there any way to stop it remotely?
Not remote.
Okay, so the way this is drawn, as is, won't work entirely. What would I have to change to get that top piece so that it would start and stop this motor?
Remove the wire in between 567.
Remove the two momentary contacts.
Yep.
The momentary contacts?
Or you remove your stop and start
Switches, the
switch.
stop
The buttons.
Yeah.
Okay,
Remove the stop
so I
and
get
start.
rid of my start and stop buttons
Right.
to make this work so that then would it be a momentary control from the front
On or
end?
off.
It'd be a sustained or a held output from the
Either
control
24
system.
volts or 0 to 10 volt control.
Anybody have questions on that? Why that would work?
But you'd also, it'd work even if you had a constant at the top, it would work the same. That's why you have your handoff auto on our buckets.
Yeah, but if we didn't have the handoff auto, this was all we had, but if you had the handoff auto, then yeah, you could take the handoff auto and turn it off that way. That's true. But if this is all we had, we would have to remove the start and stop portion of this and just wire up 5 to 7 like it shows up there with that contact. The output from the control system would be on or energized to turn it on, and then as soon as I wanted to stop it, I'd de-energize. And that would be how we would do it.
But you wouldn't have to remove the start and stop if it would stay energized all the time.
You would.
Remove the stop at least.
You have to move at least the stop.
Right.
Yeah, you have to move, because otherwise, you would never be able to stop it.
Sure.
So, yeah, so if you could just get away with removing the stop button.
You could just de-energize the control
Right.
and it
You
should
just
stop it.
command it off.
Not if the stop button was there,
Right.
because we have a holding contact here.
Change the
So-
stop button to set up contacts.
The way we could get rid of it, you
If you
could get
remove
rid
the
of
wire
this.
from 6,
Right.
if you remove the wire from 6, though, it wouldn't.
Yeah, you could also get rid of the holding contact connection. That would be another way to get rid of it so that it would work. So there's a couple ways. So good. All right. The second question is one I want you guys. Whoa. Let's see it. This was the second question already. Here's what it says. So modify the drawing so that the system, the BMS, so it can start and stop, and also keep the start-stop switch, the start-stop buttons in place.
You want a switch that tells it BMS versus local control, or do you want it without a switch?
No, so no handoff auto.
And 3-wire control or 2-wire control?
So you determine what you're going to do, but you're going to add contact or contacts, depending on how you want to do this, so that you can start it and stop it, but also let the start-stop buttons work as they are. So this wire here,
Wire it from 6 to 7.
you just work on it and you draw it up, and then we'll compare notes.
That's the answer.
Well, don't give it away. Okay, so take a few minutes and add relays or contacts where you think you need them. Okay, so how do we implement the start from our BMS? Okay, so Matt, I know you know, so we're gonna give somebody else a chance first.
To do the BMS, you'd do at 5 and 7 with the normally open contact.
So like it was before?
Yeah, just that.
So you're saying a normally open contact, like,
Yeah.
it's hard to draw straight.
I guess, I mean, if Zach's doing the wiring, then it looks like that, yeah. Don't tell
Okay.
him I said that.
So how many of you agree with that?
To start it?
It's beautiful.
Yeah, to start.
It will start it, but you
Well, no,
gotta
stop,
do better
stop,
than that if you're
stop.
gonna
No,
stop.
stop.
But it won't stop.
it. No.
Okay,
7.
so,
Local control
so
is no longer.
this could start it.
Right.
Is this maybe the best way to start it? Is there a different way?
Yeah, use 2 relays.
Okay, we'll get to the stop, but just for starting,
Yeah, through BMS, that is the simplest way to start.
okay?
Or you could
I would
just,
just put that
Parallel.
over 6 and 7, right? Parallel with 6 and 7,
Okay,
right? And
so-
you got your
Yeah,
stop
so
right
the
there.
other way that probably, this will work, but would be just slightly better as far as, and get a straight line here,
It's okay.
would be to do something like right there, okay? Because what we've done is we have a normally open in parallel with a normally open. That gives us an OR, right? That's kind of the OR condition. So either one can start. Now, is this contact going to be maintained or momentary?
momentary.
It'll be momentary.
Okay, I want you to think about it for now. Just think about it. Okay, how do we do the stop?
In
Put a parallel.
series with that stop,
Series really
make another
control
set of
it.
contacts that are only closed.
Okay, so I had 2 people at the same time.
Right.
He was like,
Yeah,
Okay,
series with the stop,
So in series with the stop,
so it'll break that circuit.
okay? So we paralleled the start, because it's normally open, and we series the stop because they're normally closed. So I'm going to draw this over to the side here,
Remove the wire between 5
and that is one ugly looking contact, but we'll say that we did something like that,
You still gotta remove the wire.
Erase
between-
that,
Yeah, there you go.
and then we get rid of that guy. Something like that, right? Okay.
There you go.
So now that we have in series, here's the question. If I'm running these contacts from the BMS, so I've got some relays out here, right? Oop, let's do that one over. I don't know why these circles got way big.
You hit shift and it makes like a perfect circle.
So there's my circles for the coils, and we could do that. She's got all the tricks. So those are my coils. So I've got 2 relays, right? What was I going to ask you? What type of, are they maintained or momentary commands from the BMS?
it would work a lot better for momentary. Because otherwise, when you stop it and release it, it starts again.
Okay. So if this was maintained, if I turned it on and I held it on, could the local stop button turn it off?
Yeah.
Momentarily.
It could turn it off only as long as they held the button in, right? As soon as they let go of the button, it would start back up. But if it was momentary, much like the buttons are,
That's right.
then we've duplicated the functionality, right?
With his finger in the dike.
Yes. Okay. So any questions on this then? Does that make sense? So now we're going to jump really quick, and we've got 25 minutes to go through this. When we talk about relays, a lot of times we're doing bigger things that we're turning on and off, right? So question 1 here, and you've got all of these questions. We're not going to go through all of them, but just to kind of give you a comparison. When we're talking microprocessors, like so for instance, in a computer, your desktop or a laptop or whatever, we have,
IAX and IAX.
yeah, there's an i7, there's all sorts of different, depending on if it's Apple or PC or whatever. The processors that we have in there have how many switches in them? How many relays essentially?
Millions.
millions, if not billions, of relays in a 2-inch square, right? They're packed in there. They've been able to build them so tiny. And how often do we switch those relays from on to off or have the potential?
2 gigahertz, 4 gigahertz.
So 2 to 4 gigahertz, and what is gigahertz? We've got 60 hertz in our wall, right? So 60 times a second. What is gigahertz?
Billions.
So billion per second. So if you can think of controlling millions and millions of switches and switching them up to several billion times a second, I want you to think about how amazing that is. We're dealing with relays that switch much slower, and we don't have very many. And I'm really glad, because the relay logic to put that all together is pretty crazy. But that's kind of the idea, is that we're dealing with the same kind of principles. We're switching, turning things on and off, right? That's all relays are doing, allowing current to flow from one place to another. Okay, so we're going to go through a couple of these real quick. So these are the one way of drawing a relay, right? It's different than the coil and the contacts we've looked at. Here again is our coil, our contacts up there. So in this case, my voltage, we're trying to get down to the output. So is the voltage getting to the output on
No.
the part with
No, it's
input A?
not.
How about an input B? On neither, right? Because just the way it stands, I've got ground there, I've got ground there. And so there's no voltage at the output. If I energize input A, voltage then, this switch comes down, voltage comes down, and it sits here,
Still low.
but still not on the output. So I have to energize input B. Can I let input A go? No. So this is an AND, right? A and B both have to be energized for voltage to get all the way to my output. Okay. We have another one here. And let's walk through this one. Very similar looking. Except voltage now is on the bottom here. Voltage is on the bottom here. If input A is energized, my voltage comes all the way down to the normally closed. Do I have voltage on my output?
Yes.
Okay. Say input A is not energized and input B is. Okay, so this is what? An OR. So either input A or input B allows voltage to get to my output. Okay. A lot of times we have what we call ladder logic. Ladder logic is a way to kind of isolate, control, kind of sequence, and to understand how it works. Our left and right horizontal or vertical columns typically represent our voltages. So in this case, L1 is the left vertical line, L2 is the right vertical line. Those could be 120 and neutral. They could be 240 volt, leg 1, leg 2 of a 240 volt or a 480 volt circuit. Okay, and so all of the horizontal rungs, as they're called, will represent the various control schemes, switching, and loads that we will then turn on and off. Now, one of the things that we want to be careful about is that we always have only one load in series. So I wouldn't want to put an indicator lamp in series with the heater, right? Because why? What would happen?
Divide the voltage.
Yeah. Both of these are designed or built to handle the voltage of that circuit. So if it's 120, the light takes 120, the heater takes 120. If I put them in series, they will
take a lot less current.
Yeah, they'll divide it because they've got twice the resistance. Current drops in half. Current's the same all the way through that rung, or that rung on the ladder. And so my light may not turn on. It may be real dim.
Well, your light would be a half amp possibly, and your heater 100 amps. So the light would light up, but the heater wouldn't get warm.
No, the light would still be dim because it only gets half the voltage drop. There's still the same amount.
It wouldn't be a balanced voltage drop though. So light would still see nearly the full.
True. You would see the current go through, but the voltage drop would be lower because the light will have a higher resistance. So your heater's not going to do anything is what's going to happen. So you're still going to get the voltage drop across each, and it won't work
You're
correctly.
basically adding the resistance for both the lamp and the heater. to get-
Heater's really
It'll burn
low,
out.
so the
Yeah.
heater's going to be really low resistance because it's going to light up.
It's cold nichrome wire.
Yeah. The lamp is going to be, it's probably low as well, but they're going to divide
Yeah,
that.
it's gonna divide it.
Okay. So that's one thing we want to avoid is doubling up loads on a rung. Okay. Let's see here. So here's one where we have that same circuit, and let's talk a little bit about what happens if we introduce a ground fault. Okay. Ground fault means the wire here somehow is rubbed, through and is touching something that goes to ground. Now, if I have 120 volts on L1 and neutral on L2, and we're, nothing's, this isn't powered, the switch isn't made, is there going to be any problems?
No.
Okay.
Not yet.
So I turn on my master control power,
Still no problem.
turn my heater on, the heater starts heating,
Still no problem.
pressure starts to build. All of a sudden, my pressure builds enough that my pressure switch is made.
You got a problem.
What happens then?
That's when you got your.
Short, right? We no longer have a load, so with zero resistance, how much resistance do these devices have? The
Zero.
switches? They're basically zero. There is probably some resistance there, but essentially in the circuits that we work with, it's so small compared to the loads that we work with that it's zero. And so if I have zero resistance, how much current flows? Infinite, or at least as much as it can until it pops a fuse or melts the wire, right? Okay. Now what happens if this is instead more like 240 or 480 volt, where I've got two legs that make up the voltage?
You're gonna have a problem with one
You're
leg.
gonna have, right off the bat, you're gonna have problems.
Okay, so what's going to happen that's different?
You gotta trip one leg.
L1's gonna trip
Will it trip?
with the ground.
So they've got a ground here. Will it trip?
The
It'll
reduced
burn
solenoid
up.
will get half
It
power.
will trip, it's
It might
gonna sense it
function.
and trip it right off.
Actually,
Yeah,
you run
your
like it's,
starting
you run like
state.
it's a 110 solenoid.
Yeah.
It's gonna
So
use
if this
the
is a
ground
240
as
solenoid, I've got 120 volts flowing there. This is going to chatter, warm up, but it's not going to trip the circuit because it won't pull enough current, right? Because of the resistance of this is built for 240 volts. Okay. Will it work right? Okay. What happens if my pressure switch makes? Then you're going to go, right? Just like the other. Okay. But if this happens and you come over here and you touch this, you may or may not get zapped, right? You're grounded, so maybe it goes right by you, but you've always got to be careful, right? What happens?
You're saying if I got 110 volts on L2 and it goes to the ground, that it's not gonna trip that circuit breaker?
No,
The
You-
solenoid
Becomes a
makes it.
110 circuit.
because it's a 110
'Cause it's
circuit
got a
through a
load.
240 volt load.
It's
But
going
if that
through the
ground
load
fault
to
was
ground.
on any of the
But that-
legs.
You
then-
have a load.
That circuit breaker's gonna see that, it's gonna trip it right out.
It's gonna act like. your
Not
neutral,
till the high
your
pressure
Facebook
switch
can act
trips.
like-
Once the high pressure switch engages it with it.
So because of this, you're going to have half the current.
I've never seen it not trip. When you take 110, take it to.
It's like if you take a.
But you're not taking 110 straight to ground. You're going through a load. So there is a current here that's dictated by the resistance of this circuit.
Maybe
So-
in a simple.
So say for
simple
instance,
Circuit like that perhaps, but everything you have on out there today has solenoids in it, has solid state circuitry devices that sense that, and it will trip it immediately.
so not your little Taco or Taco, however you say that, those little solenoids won't. They won't have that circuit breaker. Some of the bigger ones will, maybe.
But if you put that
Sense it
ground
and trip
fault
it
to the light,
Yeah,
Trip.
Yeah, it would trip.
It doesn't have enough resistance like the solenoid does.
yeah. Okay.
But if you had a 110 solenoid and it was the other way around, then
If you had this fault here with that light there, it would not trip.
Because of the resistance.
So,
It's gonna act like it's a 110 circuit,
Yeah.
because it's using like the ground.
so let me give you some numbers. So say this has 240 ohms of resistance. On a 240 volt circuit, I get 1 amp through there normally. Does everybody agree with that? On 240 volts, I have 240 ohms of resistance. So to do the math, you'd end up with 1 amp current flowing through here if the ground fault wasn't there.
Right.
So this switch is still open. I put in this ground fault. Now I have 110 volts going to ground through a 240 volt load. What's my current?
Half of that.
Half an amp. Because this load basically it resists a full flow. The lamp would be the same thing. The lamp is designed for 240 volts. If I only have 110 volts going to ground, so long as it's not this directly to ground, it won't trip.
That's why the electric motor service that used to be here in town would use a light bulb to test for a grounded motor. Because the light bulb itself limits the current, and they can put high voltage on the leads with their test probe
And it wouldn't burn it up.
without burning up wires or tripping breakers.
Yeah. Okay. And I want to make sure everybody's good with this before we move on. We all believers? Jeff's like, no.
Some ways I'll say circuit works, circuit
Well,
works.
but not-
Simple circuit, yes.
A lot of what we have on campus are simple circuits. More so as we get into VFDs and other complex, newer designs, they will have some of that other protection.
Even the new Lilies out there, they're all designed since then. Right, so.
Okay. So, moving on. So here's kind of a ladder logic, and we want to see what does this circuit represent. Is this a AND or NAND or NOR function? If I press A, if I press B, what does it take to get my indicator light on?
So you have 1 and 2
Both of
in
these, so it's, and
Okay, does that make sense? So I got AND, I see AND. If I press A, CR1 energizes, this closes, but I still have this one open. If I do it the other way, same thing. I have to press both A and B, they both close, then the indicator light will turn on. Alright, so this one here, they want us to draw, how would we implement an OR function with these two push buttons and the relays that are next to them. So Matt, if you'll pull that up a little bit. We could go this. There we go. Okay, so what do we need to do?
Put a line from A to B and put your contact, oh, sorry, I'm not bad.
There's contacts from CR1 normally open.
So we have normally open. Which one is this one?
CR1.
We have CR1.
Underneath it,
and then I normally set up closed.
Are we doing an or are we doing an or?
So this is an OR. We're trying to create an OR situation.
But
Yeah.
So you have
that's
CR1
straight
normally
another set
closed.
underneath it.
Yeah.
You want this normally closed?
No, another set.
Parallel to it. Or
Here
sorry,
or
series.
below it?
Right there, below it, right there.
Yeah, in parallel, on that one.
And that's
It's
closed.
Normally closed, yeah.
No, that's an open CR2.
That's an open one.
CR2.
CR1,
Oh, you're right.
right?
Either
CR1 you
one.
want, because
Either
you want
one.
the current to
You
flow
want
through
them
that
both
one
open.
on either one. So
You
you
want them
draw
both
this.
normally open.
Yeah, both normally
You want them both normally open. Either one
Either or.
shutting will
Will turn it
energize
on.
the circuit. If they're both.
Okay, we need a consensus.
Both open, and then if it's pushed in, it'll close either one of the contacts, either one of those pushed in.
If I do something like that,
Yeah.
Yes,
Straight into it.
yes,
Yeah, that works.
that will work,
Yeah.
yeah.
okay? So if I press A, CR1 energizes, the light turns on. Press B, CR2 energizes, the light comes on. If I press both A and B,
Still comes on.
light's on, we're still good, right? Okay. All right, Matt, go ahead and drop that down. All right. What's that one gonna do? We're really running out of time here.
So I'm gonna energize with the CR2.
A is the not. So,
So tell me which one of these four give me an indicator. First, second, third, or fourth?
The second one.
Second. Second one,
Okay, the second one, right? If I press B, CR2 energizes, I close, the light comes on.
Right.
Anytime I press A, it opens it.
Mhm.
Anytime they're both, just like they are, if they're both off, then it doesn't work. Okay, I think you guys are getting this. There is a page here, we're not gonna spend time for you to work these out, because we don't have enough time right now. But let's just, I'll tell you what they are, and then you can go back through and verify it later. We'll do it together. First one, what does that look like?
Yeah.
An and, right? So,
That's the fourth one.
so both A and B have to be energized. And the second one, so going across,
Or.
that's an or. So we've done those two a couple times now.
0, 1, 1, 0, both 2 and 3.
So what about the third one?
Not or. Nor.
And or.
Okay, the very
Or
top
not.
part, right, looks just like the one we just did, but then the bottom inverts it.
So it's not.
So it's a nor, okay, so a not or a nor. Okay. What about our fourth one here?
Not and.
Still or.
But still. It's
Not
one.
or.
You have to have them both pushed in order to get the light off.
It's
So
Right.
it's a not and.
It's a 1 0 0 0 0.
So I'm 1 1 1 0, right? So that's a NAND, a not and. Okay. This one here. What is this top part?
Or
and.
it's an and.
That's an and. We invert it.
Convert it.
So it's another NAND, right? So those two are identical in function. They're done two different ways, right? Okay. Which one's cheaper? Right? We didn't use a relay. We're saving the environment, right? One relay at a time. Okay, what's this one here?
It's good.
So what did you label that middle one then?
So it's an and.
Nan?
It's in
Both of them, yeah,
Well,
okay.
The natural state is the only way to get the light to stay on.
So it's 1
0,
0 0 0. We look under thing, that's a NOR.
It's a nor.
We had a NOR right above it, right? So this was a NOR and that's a NOR?
Yep.
So again, two different ways to do the same logic. One uses an extra relay than the other one. Okay. These last couple are kind of the ones we haven't spent a lot of time with. Right now,
We're talking exclusives here.
yeah, so this gets into our XORs or XNORs, right? So the way it stands,
Lights on.
lights on. If I press one of the two,
It doesn't matter which one lights off.
yeah, but if I press them both,
Lights on.
okay, so I'm a 1 0 0 1.
So it sounds like a not exclusive or.
Yeah, so XNOR is that one. So what do you guess this one's going to be? So right now, are either light or is light on for zeros? I don't have a path for either, right? So I'm 0. I press A or press B,
Yep,
lights on. Press A,
yep,
lights on. Press them both,
no.
flips those two, and they turn off.
So that's an exclusive.
So that's an XOR. Yeah. And then the last one's just a simple invert or a not. So basically I I have a true coming in, I have a false going out, or vice versa. Okay. Now, really quickly, there's a couple troubleshooting ones. I'd like you guys to just look those over, and there's a couple, just think about some of the scenarios. But one I want us to do real quick, and I know we're running out of time, is question 16.
Second to the last page.
So what this one involves is using the ladder logic diagram above and then drawing in the lines on our terminal strip and our relay base. Now, just so that you understand, on the relay base, this is my coil, the little curly Q wire in the middle. The coil wires come to the top outside corners. So these outside corners are my coil connection. The interior, or the two at the top in the middle, are the commons for each of the two contacts. So those come down and they come to the normally closed. The normally closed are the interior ones. Normally open are the outside on the bottom.
And your battery symbol at the top, very top,
Yeah.
is positive on the right?
No. Little positives on the left.
So positive is on the left as you're looking at it. Negative on the right. I didn't draw it.
Okay.
The negative, we're gonna have to jump
Put a
wires.
little plus on that.
What's that thing on the bottom?
Which
Motor.
That's a
It's
motor.
the motor.
That's a 150 horse motor right there.
Sure.
For DC.
No.
I can imagine. DC
No
motor.
overload.
Yeah, it's,
With no overload.
okay, so take a minute and see how you'd wire this up, and then we'll quickly go through it. So up here where our battery is, we have a plus and a minus. That really,
Backwards.
okay.
That one's now plus, that one's now minus.
That's why you only jump
Great.
twice.
Now you're gonna let the smoke out.
Okay.
And
Twice as
negatives,
fast.
negatives on the
So
wrong side.
one of the things that I like to do is if you get the simple side done first, that's going to be our negative side, right?
Yeah.
We have two loads, so we're going to connect those two. So here's our negative right here. Where do we want to go first with that?
Tier
One
one.
coils.
So the coil, where's my coil connections again?
Outside
Two
of
outside, two
Top
outside.
corner.
Top here and there. Which side do I want?
You go left side, go. Doesn't make
Oh.
any difference.
We'll make it easy and just go like there, right?
Yeah. You
Then
come
you
off
gotta
of
go to
that,
the motor.
come off that.
I also
go to the
want to go to
motor.
the motor.
Okay, so we need the negative side of the motor.
Yeah.
So can I come from here or here?
Doesn't
Either
matter.
place, right?
Yeah,
Or in the
doesn't
middle.
matter.
If it's really 150 amp or 150 horse motor, this ain't gonna work, right?
No.
But in this
Okay,
case,
go forward.
we'll do,
Actually, the bottom one.
you want the bottom one instead?
No, that's
Because you're not
good.
jumping over one.
Let's go with that.
Okay. That's right, we can do the bottom. We can erase, it's easy. Okay,
Okay, now it's done.
okay, so there's our, this side and that one done, right? All of that, those wires are done.
Motor
Okay.
goes to CR1. One way to-
Jump from start to stop.
So we got our plus now. We're gonna go from our positive side. And where's that coming first?
Start the start button.
Okay, it's coming down. And it's gonna get our start.
One goes CR1 open, one way open, CR1.
And the
Okay, it's gonna go to,
CR1
two
and CR2.
commons of.
It's gonna go to both comments.
Yeah.
okay, where are our commons?
Looks like they're on top.
Your comments are on the bottom.
Inside middle.
Top middle.
Top.
Commons are up
Middles.
here. Normally open, normally closed, normally closed, normally open.
Okay.
So we can. Something like that.
Sure.
Okay. So that takes care of that one, and that one there, right?
Yep.
Okay, where next?
Start
One
to
open,
start to
one
stop.
closed, stop.
So start to our stop.
Yep.
Yeah.
And tie that one also to the left normally open.
Contact.
So that one right there?
Yeah.
Yep.
Looks good.
Everybody like that so far?
Excellent.
Come off the stop.
Okay,
go to CR1.
so that takes care of this and those, right?
Yep, just come out,
Okay,
come out
right
the other side of
normally
the stop
open.
and go to the other side of the coil.
So that's going
To the other side of the coil.
right there, right?
Yeah.
So this one could be fun.
Take a trip.
Yeah, take it on a trip around.
Okay, we'll do it that way.
Okay, now power the motor, the other, the right normally
There
open.
you go. That goes down to the motor. Okay, you're done.
Okay. Everybody see how that kind of goes?
Yeah.